So in this video, I introduce improper integrals. To this point in our experience, we have only considered integrals with at least the following properties. Of course, there's more, but at least this much. One is that you're integrating over a bounded interval from a to a b. In other words, the interval is not infinite. So that one of the bounds is not infinity. And the other is that the function's values on the interval itself are bounded, which means the function does not contain a discontinuity, where at that discontinuity you have a vertical asymptote. But in practice, though, we might encounter integrals that lack one or actually both of these properties. So as an example, this integral comes in quite useful in a couple applications, even though the integral is from 1 to infinity. And then you have this integral from 0 to 2, and yet notice the function 1 over 2 times the square root of x is not defined at 0. So integrals that don't have one of those two properties are called improper integrals. And it's easier just to show you an example of how to go about evaluating them instead of going and giving you the overall general viewpoint first. So let's suppose that you have a region that lies under the curve 1 over x plus 1 quantity squared that also lies in the first quadrant. I've shaded in the region that's important. Notice that the region is unbounded. That means that the shape is infinite in size. It goes to the right forever. So most people look at that and say that the area that you see in blue must be finite. But also compare that with the definite integral from just 0 to a b, where b is just some positive number. Well, it seems reasonable that the area in blue is certainly more than the area in orange, but as b were to grow and increase without bounds, that the orange area would sort of eat up the blue. So if there is a value for the definite integral from 0 to infinity of 1 over x plus 1 quantity squared dx, again, that's the area of the region in blue, it should be the same as just taking the limit of the definite integral from 0 to b of the exact same function dx, just as b increases without bound. Because again, it's as if the orange region sweeps out the blue. Now, if we just continue with this particular limit, we would do the definite integral first, which is very easy. We could find that antiderivative and evaluate the bounds. But once you do so, now you take the limit as b were to grow without bound, and that limit is 1. So surprisingly, even though this region is unbounded, it actually has finite area. Now that you've seen one example of an improper integral, let's just define those particular types. So for now on, if you see an integral with infinite limits of integration, they're just called improper integrals of type 1. And there's a couple variations, so I'll define all of them right now. If a function is continuous on the interval from a to infinity, then we can define the definite integral from a to infinity of that function dx to be the limit as the upper bound in the integration increases without bound of the exact same integral from a to b of f of x dx. Notice that means in the integration, the a is a constant, it's something that's known, the b is a variable. You do the integration first, and then you do the limit. You get similar definitions if you're going from negative infinity to b. And if you have a continuous function on the interior real line, then you can define the definite integral from negative infinity to infinity of the function as the sum of two of the previous integrals, one from negative infinity to a c and the other from c to infinity, where the c can be anything you like. Now, all of these make sense only if the limits exist. So if the limits exist and they're finite, then we say that the improper integral converges and the limit is the value of the improper integral. So the improper integral can have a value. It's just found through a limit process. If the limit fails to exist, then the improper integral is considered to diverge. In the last one, the definite integral from negative infinity to infinity, it's a sum of two other improper integrals. If either of these two new improper integrals, where one of the bounds is the constant c, if either of those diverges, then the original integration from negative infinity to infinity also is considered to diverge. Alright, so let's go ahead and do an example. This would certainly be an improper integral of type 1. So I'll write this instantly as the limit as b approaches infinity of the integration from 1 to b of 1 over 2 times the square root of x dx. This would then be equal to, that's the limit, as b were to increase without bound of, that antiderivative is very easy to see, it's just the square root of x, and we would then evaluate that from 1 to b. So we do the evaluation, then the limit. So that's equal to the limit as b were to increase without bound of, that would be the square root of b minus 1. That limit does exist, it's just infinite. So while the limit exists, it's not finite. So we say that the definite integral from 1 to infinity of 1 over 2 times the square root of x dx, we say that diverges. Now notice though that the function is positive, so there is a region below this curve and above the x-axis from 1 to infinity. You could then say that that area is infinite because of the limit process I just did. Let's do another example. In this case, we once again have an improper integral of type 1 since the bounds have infinities in them. So in order to find this particular value, I'll break up this integral right away around some value. And I can pick anything I like. I'll pick 0 though, mainly because it's a nice number to work with. So I then have from 0 to infinity of 1 over x squared plus 1 dx. So this will then be the limit as a approaches negative infinity of the integration from a to 0 of 1 over x squared plus 1 dx. I'll do that limit afterwards. And then I'll add to it the limit as b were to increase without bound of the integration from 0 to b of 1 over x squared plus 1 dx. Oh, I shouldn't have that parenthesis there. Actually, let's get rid of that. And that one there too. The parenthesis should be here and here. There we go. So that then is equal to the limit as a were to decrease without bound. That is the arctangent of x. We evaluate that from a to 0. That's plus the limit as b were to increase without bound of, once again, the arctangent of x as we evaluate that from 0 to b. That is then the limit as a were to increase, well, decrease without bound of, well, it would be the arctangent of 0, which is 0, and the arctangent of a. So I have the negative, the arctangent of a, and then I'd have plus the limit as b were to increase without bound. That would then be just the arctangent of b. So I'd have arctangent of b. This first limit is the opposite because the first negative. And if a were to decrease without bound, the inverse tangent approaches a negative pi over 2 plus. If b were to increase without bound, the arctangent of that b would then approach pi over 2. So notice that since each of them converge and are finite, the original integral also converges, and it converges to their sum, which is pi. That's the answer. That's very interesting because that means that the area underneath this graph and above the x-axis over the entire real line, even though the region is unbounded, the total area is finite. It's only pi. Let's do one last example of an improper integral of type 1. Now there are plenty of integrals where all you really care about is if the integral converges or not, if it has a limit and it's finite or not. So here, let's look at one such problem. Let's pretend that we want to look at the improper integral as we integrate 1 over x to the p as the bounds go from 1 to infinity. Let's look at a couple simple cases first. What if p here was actually 1? Then in that case, the integration would be 1 to infinity of just 1 over x dx. And that would be equal to, now normally I should put in the limit as b increases without bound of the integration from 1 to b of 1 over x dx. But you'll notice that many people will then kind of cheat with the notation and will skip that step entirely. And instead, they won't write that. And instead, they'll just find the antiderivative first, which is in this case the natural log of the absolute value of x. And they put the bounds down. Now the bounds should be from 1 to b, and on the outside, they have the limit process as b were to grow without bound. But again, many people will actually skip that step and just remember what it means. So here, they'll put infinity instead. And remember, that means that x is approaching infinity. So you have to do a limit process to find out what should go here. So you just can't plug in infinity. So the natural log of x in absolute value, as x goes to infinity, that would then be infinity. You then have minus the natural log of 1, and that, of course, is infinite. So that would then say that in the case where p is 1, the improper integral diverges. Let's see now the case if p is not that. So what if p is just not that? So first, what if p is more than 1? Well, if p is more than 1, then you'd have that the integration from 1 to infinity of 1 over x to the p dx is the same as the integration from 1 to infinity of x to the negative p dx. And using that little notational trick, that's the same as writing, I find the antiderivative first. So I take the x, I increase the power by 1, I multiply by the reciprocal of that particular power, and I evaluate from 1 to infinity. Now, if p is more than 1, then this exponent is negative. So you have x to a negative power. If x were to increase without bound, where this is a negative power, this portion would go to 0. So the first part would be 0, and then you have minus. When you plug in 1 for x, 1 to anything other than some silly things, would then of course be 1. So that would be 1 over 1 minus p times 1. And that is 1 over p minus 1. So this particular improper integral would converge. So in this case, the improper integral converges. And its value is 1 over p minus 1. If you want to trace through it all over again, what if p is between 0 and 1? Well, then all the steps I just did are still true, except for right here. All of this would be exactly the same. I would eventually get to 1 over 1 minus p times x to the 1 minus p, where the bounds are going from 1 to infinity. And remember, the infinity means x is going to infinity. Since p is less than 1, this exponent here is positive. And if you take x to a positive power, but where the x increases without bound, the expression goes to and increases without bound also. So then in the limit, you now have infinity minus 1 over 1 minus p. And this time, that's infinite. So you could then get a nice little rule. It converges if p is more than 1. It will diverge if p is more than 0 but less than or equal to 1. And in fact, when it converges, you know what it converges to. It has to converge to 1 over p minus 1. So the type 1 improper integral corresponded to when the integration bounds were at least infinite on one side or the other, or maybe both. The other one was where we had discontinuity, or in particular where the function was unbounded. So we'll say integrals of functions that become unbounded within the bounds of integration are called improper integrals of type 2. And where the unboundedness occurs in the bounds of integration will change the way we define the improper integral. So if the function is continuous from the closed interval, well, half-closed interval, from a to b, but discontinuous at b, then the definite integral from a to b of f of x dx is the definite integral from a to c of f of x dx, but where c is a variable and c approaches b from the left. Now, from the left is important because c has to stay inside the bounds of integration at all times. So if c is between a and b, that means c is less than b. So c must approach b from the left. You get a similar definition if the function is continuous from a to b. It's continuous at b from the right, but discontinuous at a. Then the improper integral from a to b of f of x dx is defined in terms of a limit. Notice that c is now the lower bound of integration, and c approaches a from the right. It's important to be from the right because c is between a and b, and therefore c is more than a at all times. If you have a continuous function, but it's not continuous at some value inside the interval, then we can still define the definite integral from a to b of f of x dx as the sum of two other improper integrals, where it's broken up at the discontinuity. In each case, if the limit exists and is finite, we then say the improper integral converges, and that the limit is the value of the improper integral. If the limit fails to exist, then we just say the improper integral diverges. So if the limit exists and is finite, then we say that the improper integral converges, and if the limit doesn't exist or is infinite, then we say that the improper integral diverges. Just like last time, notice that the integral where the discontinuity occurs in the middle forces us to break that improper integral into two other improper integrals. If any of these diverge, they all diverge. Well, if the left or the right from c, if either of those integrals from a to c or c to b, if either of those diverge, then the integral from a to b will also diverge. So if you're just looking at this integral, you'll notice that the function 1 over 2 times the square root of x is actually discontinuous at 0. So this would be an improper integral of type 2. It's unbounded at one of the endpoints or somewhere in the middle. So I can write this as equal to, that's the limit, as a would approach 0 from the right of the integration from a to 2 of 1 over 2 times the square root of x dx. Now from here, this would then be equal to the limit as a approaches 0 from the right of, that's just the square root of x, and I would evaluate that from a to 2. And that is the limit as a approaches 0 from the right of, that would be the square root of 2 minus the square root of a. And this limit, now notice the normal everyday limit of the square root of x as x were to just approach 0, that does not exist. And it doesn't exist because the square root function doesn't exist for all values around 0. It only exists for numbers to the right of 0 or at 0 itself. So if I did not have the limit from the right here, the answer would be the limit doesn't exist. Here though, since I am coming from the right, I know the square root function is continuous at 0 from the right, so I can just plug in 0. And the answer is the square root of 2. So since the limit exists and it was finite, I can now say the improper integral from 1 over 2 times the square root of x dx converges, and its value is 2. Well, square root of 2. Oftentimes we shorten this and say that the improper integral converges to the square root of 2. Let's do another example. This particular function would then also be an improper integral of type 2 because it's discontinuous at one of the endpoints, in this case 1. So I'd be forced to go and write this as the limit as b approaches 1 from the left of the integration from 1/2 to b of 1 over x, the natural log of x dx. That particular integration would then be the natural log of the natural log of x, evaluated from 1/2 to b, and the natural log of x would actually be an absolute value. And that would then be, you then have the limit as b approaches 1 from the left of, I'd have the natural log, absolute value of the natural log of b, then minus the natural log of the absolute value of the natural log of a half. Now that would then be, well, if though I allow b approach 1 from the left, the natural log of that would of course approach, well, 0. And if this is approaching 0, and it's always more than 0 because this is never actually negative, right, because of the absolute value on it. So I have the natural log of a positive number, but it's approaching 0. So then this, therefore, goes to negative infinity. So that would be negative infinity. And the other would then be minus the natural log, absolute value of the natural log of a half. And we don't really care what those values are because it's clearly just negative infinity. So we're forced to say that the improper integral diverges. So the improper integral from 1/2 to 1 of 1 over x natural log of x dx just plain diverges. Now this particular example is here in order to prevent you from making certain assumptions. A lot of the rules that you would expect to be true are actually not true because we have a limit process involved now. So for example, if I want to know what this improper integral would be, I would notice it's of improper integral of type 2 because there's a discontinuity in here when x is 0. So, but what if you said, I don't care. I bet you it's okay. Let's just go ahead and find the antiderivative like you always would. It's really x to the negative 3 from negative 1 to 1 dx. That would then be you take the x, you increase the power by 1, you then multiply by the reciprocal and evaluate from negative 1 to 1. This would then be negative 1 over 2 times x squared. That's evaluated from negative 1 to 1. If you plug in 1, you would then get negative a half minus. If you plug in negative 1, you still get negative a half. So you say the answer is 0. But then you would then come back and look at the graph just to check it. And you'd notice the graph of 1 over x cubed looks sort of like this if I had drawn it really well, which I really probably didn't. And you're going from 1 to negative 1. So you would probably try shading it in. You would look at it and go, oh look, the area here and the area here, those regions are actually congruent to each other. They're the same region, just kind of rotated. But one's above the x-axis, one's below the x-axis. So I know from before that when that happens, the definite integral should be 0. So then the answer must be 0. I have now confirmed it 2 different ways. That's all wrong. That's unfortunately wrong. Because what you need to do is you have to take the integral from negative 1 to 1 of 1 over x cubed dx, and you must break it where you have the discontinuity. In this case, from negative 1 to 0 of 1 over x cubed dx, plus from 0 to 1 of 1 over x cubed dx. If either of these new improper integrals diverges, then the original one diverges also. So let's just look at only what if I went from 0 to 1 of 1 over x cubed dx. That is the same as the limit as a approaches 0 from the right of the integral from a to 1 of 1 over x cubed dx. And that's the same as writing the limit as a approaches 0 from the right of, well, we already know what that antiderivative is. It's negative 1 over 2 times x squared. And we're just evaluating it from a to 1. So just plug in 1. You get negative 1/2. Then subtract what you get when you plug in a. That'd be then plus 1 over 2 times a squared. And we're still taking the limit as a will approach 0 from the right. Well, clearly this is just a constant, so that would be just the constant. But the second limit, though, if a is going to 0 from the right, the denominator is going to 0, the numerator is not going to 0. So this is infinite. So it diverges. And since this one diverges, I don't even have to check that one. I don't care. this one also diverges. So from this work, the correct work, I can then say that the integral from -1 to 1 of 1 over x cubed dx, that just plain diverges. So don't use your intuition, use the definition. Now that you're aware of the definition and how important it really is, sometimes though we simply can't determine the value of the improper integral by appealing to that definition. In those cases, we just try to determine if the integral converges or not, if there is a limit or not. So, to do so, we use what's called convergence theorems, and there's two of them. The first one's called the direct comparison test. So we have assumptions, and they are that the two functions are continuous on the interval from a to infinity, that their values are always at least positive, or 0, and that the values of f of x are always less than or equal to the values of g of x for every single x value in that interval. If the improper integral from a to infinity of g of x dx converges, then the result is that the improper integral from a to infinity of f of x dx converges also. We use this thing by saying that if the function g dominates, bounds the values of f of x, then knowing the bigger function's values when you integrate will converge means the lesser function values will also converge. You can then, if you have that statement, you automatically also get the contrapositive. Now, seeing why this should be true is very simple, but I think you might need a picture to remember the result. So here is ground. Here is the beginning of a wall, and then you have some wall of varying height that goes off forever to the right. So it's considered to be unbounded. You have a function, in this case a person, let's call it person G, who comes around and paints the wall. He paints the whole thing. Now you may wonder then, did he use a finite amount of paint or did he use an infinite amount? Well, but before we even can check, some smartass comes around and says, you know what, I'm gonna paint over what you did. But the guy's shorter, and because he's shorter, he can't actually reach to the same height that G did. So the top is the graph of y equals g of x. The bottom here, that's the graph of y equals f of x. If G paints a finite amount of area, that means the area of the whole region I just covered in is finite. But then clearly the other region is contained in it. So the entire area that F paints would also be finite. That's exactly what this says. If G paints a finite area, then F paints, because it's less, a finite area. Number 1 is true, 2 is true because it's just a contrapositive. So for this problem, the only thing I'm interested in is if that converges or not. Because of that, I don't have to find an antiderivative. I just have to answer the question, does it converge or not? So to do that, note the following. Note that if you look at 1 over x cubed plus 1, it's always less than or equal to 1 over x cubed, because x cubed plus 1 is a larger denominator compared to x cubed. So this fraction must be smaller than that one. And that's for all x greater than or equal to 1. Also, the integration from 1 to infinity of 1 over x cubed dx, that's a problem we've already done. We know, in fact, it converges. I even know what it converges to, but I don't really care. But I know it converges to 1 over p, which here is 3, minus 1. So that's 2. It converges to a half. So, by direct comparison, the integral from 1 to infinity of 1 over x cubed plus 1 dx, this also converges. I just don't know what to. It could converge to a half, but it's incredibly unlikely. It's just probably less than it. It's more than 0, but it's somewhere between 0 and a half. Now, the direct comparison test is usually the first thing we try if you just want to know if the integral converges or not. But there's a disadvantage with that, is that you have to come up with an inequality, which means you have to come up with another function on your own, and you have to convince yourself that one function's value is always greater than or equal to another, and that means establishing an inequality, which most students really struggle with. So if you don't want to deal with that, there is another way to go around it, and that is, well, you can try using a limit instead. This is called the indirect comparison test. The assumptions are, let f and g be continuous functions like before, and positive just like before, on the interval from a to infinity just like before. But then assume that the limit of the ratio of the two functions as x increases without bound exists and is finite. If that's true, then you get an even stronger result than before, because you can say that these two integrals, these two improper integrals, either both converge or both diverge. So once again, let's look at this particular improper integral and try to determine if it converges or diverges. I don't care what the value is. Well, to do so, I would probably reach right away and look at the particular integrand and notice that if I took x, the square root of x squared minus 1 over x squared, that's certainly less than or equal to just the square root of x squared all over x squared. And that's the same as writing just, x, that's x over x squared, because in the integration bounds x is positive, and that is just 1 over x. All right, great. So that looks like I have an inequality. So just note that would be true, and that's 4 x is greater than 2. Then I would look at the integration from 2 to infinity of 1 over x dx, and that's one of those improper integrals I've shown you before. That was where I had 1 over x to the p. This thing automatically diverges. And that's because as p here equals 1. Well, that's terrible. Because see, if we want to get that this were to diverge because this diverges, I would then need that this integrand is more than this. It's not, it's less than it. So unfortunately, the direct comparison test failed. Direct comparison test failed. And it failed because while I just showed you that this integral diverges, I have the inequality in the wrong direction. If I want to show that this integral diverges, I need to show that this function is actually more in value than this man. So that if this man paints an infinite area region, then the guy who paints more, so it has to be more, that guy who paints more would also paint an infinite amount of area. So that test failed. But you know what? 1 over x feels really, really like a good idea. So I won't try direct comparison. I'll try limit comparison. So instead, let's look at the limit as x were increased without bound with the ratio of these two functions. So I'll have the square root of x squared minus 1 all over x squared. Further divide by 1 over x. That's the limit as x were to increase without bound of, well, that's just the square root of x squared minus 1 all over, that's just x. And that limit, I think you can tell very quickly that that limit must be just 1. Since that limit is 1, then these two integrals either both converge or both diverge. Since one of them diverges, the other does also. So I can then say the improper integral from 2 to infinity of the square root of x squared minus 1 over x squared dx. This thing diverges by indirect comparison. And that's it. That gives you a basic introduction to improper integrals. You'll see these a lot in applications, especially in other subjects, but we won't use it too often.